Start by we don't need that yet. Let me start by giving a quick recap of where things left off yesterday. Okay. So the first main point is that we're switching our perspective from thinking about time-independent static Hamiltonians to Hamiltonians that have a periodic dependence in time. Okay, so you go from h of t plus t to h of t. This defines a frequency given by the time period. The object that we study the properties of is the time evolution operator now. Okay, we don't have a static Hamiltonian anymore. The time evolution operator is defined in the usual way as the time-ordered exponential of the time-dependent Hamiltonian. Because of the time dependence in the Hamiltonian, energy is no longer conserved, but instead, because of this periodicity, it gets replaced by the notion of quasi-energy, which is defined modulo omega. And the eigenspectrum of the Floquet unitary, which is the time evolution operator over one driving period. These are these states, eigenstates alpha and eigenvalues, which are these phases with epsilon alphas. These determine the stroboscopic properties of the system. Okay, so if you want to study the dynamics of the system at integer multiples of the driving period, then all you need to know are the eigenvalues and eigenvectors of this object. Okay, and we can use these to define Floquet eigenstates, which are the solutions of the time-dependent Schrodinger equation. Okay, so this is the new framework in which we're thinking about this. Then we spent a bit of time thinking about how non-interacting band topology changes in this Floquet setting. So what we found is that when your single particle energies are no longer good quantum numbers, but only defined modulo omega, so that energy also lives in this Floquet-Brillouin zone, what we found is that you can get new kinds of topological band structures in the non-interacting Floquet problem. Okay, and this happens when epsilon of k wraps around the Floquet-Brillouin zone. Okay, so this was dispersions that are not allowed in a static problem, but could be allowed in a Floquet problem, which say look like that, and going from minus pi over t to pi over t. Okay. These can allow for new kinds of Floquet phases, for example, systems which have anomalous delocalized edge modes in systems with the boundary, even when all bulk bands have zero Chern number on the system with closed boundary conditions. Okay, or you can get Majorana edge modes at quasi-energy pi over t rather than zero Majorana edge modes, which is the more common scenario. Okay, so if you didn't catch all of this yesterday, that's okay. All right. What we're going to need, unlike the static problem where non-interacting band structure continues to be very predictive even after you add in interactions because you have a notion of a gap in adiabatic continuity, for the Floquet problem, once you add in interactions, in the asymptotic limit, everything just heats up, and this non-interacting band classification really doesn't tell us very much. Okay, so this is interesting in its own right, but in the next two lectures, I'm going to switch gears and talk about the many-body problem. So if you didn't catch all of this, that's okay. All right. And so where I'll take off today is this discussion we were having towards the end about the Floquet-Magnus expansion, or this notion of a Floquet-Hamiltonian. Okay. So formally, we can always define a static Floquet-Hamiltonian by writing it as the operator, by just in that way, that the time evolution operator over one period, we can think of it as being generated by this time-independent Floquet-Hamiltonian. This is not unique, because if you take the logarithm of this operator to get h Floquet, you have this choice in this branch cut for choosing the logarithm, so these epsilons are only defined mod omega. We can Taylor expand this equation, which is the time-ordered exponential and the actual simple exponential, and equate this order by order. This gives us what's known as the Floquet-Magnus expansion in powers of 1 over frequency. Okay, so this is a general expansion of this form. This n goes from 0 to infinity. This is 1 over omega to the n, and this is the nth term in the Floquet Hamiltonian in that expansion. The leading order piece is the simplest one. It's just the time average. Okay, so that's just h naught. This is what we'll call h naught, and this is just the time average of h of t over one period. The higher order terms end up involving these kinds of nested commutators. Okay, so each nth order has n integrals. Okay, so that gives you n powers of t. There's a denominator here, which is t to the n minus 1. So the nth term in this series gives you 1 over omega to the n. Okay. And because of these nested commutators, higher order terms have more and more commutators and they're longer and longer ranged. Okay, so in general, this is a quasi-local expansion. Yeah.
Can we ask two questions when it comes? So
sure.
Is this a definition or a reduction? So how HF is defined? Like, do you define it as such? Is it a definition related?
It's a definition. Okay. Yes.
The second is when it boils down to the Magnus expansion.
Yes.
I guess it becomes three-diagonal block matrix. So
yes.
If we populate more and more of diagonals,
yep.
what would the effect be on the quasi-empty spectrum? Like intuitively, could it give like an intuitive argument?
Yeah. So, okay, so the picture that I was describing yesterday was an intrinsically single particle picture. Okay, so that's not necessarily what happens once you have many body, but this framework is more general. Okay, so you're asking what's the intuitive picture. Okay, so first, the fact that this Hamiltonian was tridiagonal, right, that was coming from the fact that we had a delta cosine of omega t driving, so then you connected. It was tridiagonal in this kind of larger space. Okay, so let me write some things here and then we can erase it. So yesterday I had a description where we were working in this effective replica space, okay, and there in this replica basis, your Hamiltonian looked like, you know, this was H naught, this is H naught plus m omega, that's H naught minus m omega, and so on. And then these tridiagonal pieces were the coupling with delta cosine omega t, okay? So intuitively, the picture you should have in mind here is when we're doing single particle problems, suppose we take the spectrum of H naught, and the spectrum of H naught has some shape and some energies, okay? Now, this spectrum has some bandwidth, okay? The bandwidth is W. And let's consider two cases. Let's consider the case when omega is actually smaller than W, okay? So then what ends up happening is, what we're doing in this repeated zone scheme is we're taking the original spectrum and we're taking all translates of it by plus m omega, right? So you take this and you keep repeating it, shifting it over, okay? So as you shift it over, you know, so suppose that's omega. So this is the one that's shifted over by one copy. That's shifted over by two copies. That's shifted over by three copies.
Okay. So that's instigated only by the diagonal so far?
That's so far only the diagonal. Exactly, exactly. And now you have this piece and this gets shifted over and that gets shifted over, okay? So what you do then is, you know, you can either think of it as shifting things in this way, or you can think of it as taking your original spectrum of H naught and folding it into a band of size omega, okay? Because by the time you're done moving everything, you can restrict your attention to just one zone, that's omega, okay? So now what happens is this is just the diagonal piece. Now you have off diagonals, okay? So these guys are actually coupled to each other. So you start opening gaps, okay? So your actual flow K eigenstates, which you're going to get by solving this problem, is going to be some mixture of states that in the original undriven problem differed by multiples of omega, okay? And depending on how many multiples of omega you take, that depends on how many, to what effective order in this off-diagonal hopping you have to go to. Because if you only connect things that differ by a single frequency, then they're connected at first order in delta. But in general, if you bring things into resonance that differ by m omega, then you have to go to mth order in this off-diagonal piece. So the gap opening will be correspondingly small, okay?
Is this the crux of the Magnus expansion then?
This is related to it in a sense I'll explain, okay? But the crux of it is, if you want to know in the presence of driving, how are your flow K eigenstates modified, okay? What this is saying is that when your frequency is small compared to the bandwidth, you have a significant modification because you're bringing things into resonance, and once you bring it into resonance, the things that mix and give you the new eigenstates differ by multiples of frequency, and you get this heating, okay? Now consider a different limit. A different limit is we have omega being much, much bigger than the single particle bandwidth, okay? So now what ends up happening is you had your single particle band structure, and you moved it by omega, and you moved it by 2 omega, and you moved this by 2 omega. But now notice that nothing got brought into resonance, okay? So now you have this, okay? You still have the off diagonal, so things still get weakly dressed when you're getting the exact eigenstates, But to leading order, your system actually looks like it's just being, it's just the diagonal. But it's just the diagonal part, and more importantly, it's just the diagonal part within this bandwidth of omega, right? So the point is that, so this was W, that was your whole single particle bandwidth. And if omega is much bigger than W, if that's omega, right, then you don't even have to think about this Floquet problem to a leading order, okay? You can just think about the undriven system, and that's a good approximation, okay? So when this is the case, then your Floquet-Magnus expansion is actually convergent, okay? And this is actually what is used in a lot of experimental techniques to engineer a desired H naught, okay? Because what we've done is we've written H of t as H naught plus V cosine omega t, okay? Or H of t plus V of t, where this is the periodic part, and this is the time averaged part. So in an experiment, you might often have the case where you want to engineer a given H naught, which has some properties, but you don't directly have access to that H naught. But what you can do is, piecewise or in continuous time, look through various different Hamiltonians so that the time average of those Hamiltonians gives you the desired H naught, okay? And then that gives you a good way of getting about this, okay? So this is pictorially what's happening in the non-interacting limit, okay?
Sorry,
yeah. Yeah.
Convergence of the Magnus expansion
yes.
is regressing.
Exactly. So convergence, so now that was the next thing I was going to write, so this is good. So convergence of the Magnus expansion will mean, that expansion is written as a series there, and you want these successive higher order terms to get smaller and smaller, okay? So what you want for this Magnus expansion to converge in some colloquial sense is you want the norm of these operators that are existing to be much, much bigger than omega, okay? And the point is that this scales as the bandwidth, okay? So in the single particle problem, we have two cases. So case A is we can make omega much, much bigger than, let me call this the bandwidth, which is order J. J is just some term in the single particle Hamiltonian.
Is the norm much bigger than omega?
Sorry, this should be opposite. Yeah, good. Yeah, great. So we can make omega much, much bigger than J. Okay, and then your dynamics look like the leading order. They're generated by by this time average Hamiltonian. This is convergent, and this is what we were calling Floquet engineering. Okay, so this is very useful from a practical point of view, but in principle, this tells you that the properties that you care about can be thought of as being generated from this static Hamiltonian. And we already know the kinds of things that static Hamiltonians do, okay? So this is not giving us intrinsically new Floquet physics. It's just giving us the physics that already exists for the space of static Hamiltonians. So the more interesting case in the single particle problem is, say when omega is the same order as J, okay? So the Magnus expansion now is not convergent, as written. And in fact, all the interesting examples that we discussed yesterday, which had to do with this anomalous Floquet edge state or the pi Majorana mode, all of those had couplings that obeyed this, okay? So when you want to get new kinds of Floquet physics, you need this, but then your Magnus expansion is not convergent. What you can do, so this Magnus expansion not being convergent can mean one of two things, okay? One is that you're just getting heating in this single particle bandwidth space, and you're just getting something that looks trivial. You're just getting a trivial kind of heating in the single particle space, and you don't have any interesting physics. Or it could mean that when omega is order J, you actually have this kind of new interesting Floquet phase, like the ones we studied yesterday, okay? So in the latter case, what you can do then is this expansion, right, to get this Floquet Hamiltonian. The Floquet Hamiltonian is not unique, and the expansion for it is not unique. And you have various changes of frames and choices of gauges that you can do this expansion in. Those I won't go into details about. But the point is, when you have new Floquet physics, there is some choice of frame. There's some frame that you can rotate into. And in this rotating frame, there's some high frequency expansion, which ends up being convergent. Okay, so what you do is you have these terms which are high frequency, which is the fast part of your drive. You go into a frame where this fast part of the drive is eliminated. Then in this new frame, it looks like omega is much, much bigger than J, and then your Magnus expansion can converge. So when such a frame exists, that's when you get these new kinds of flow K phases, okay? But now let's move on to the many body problem, which is what we'll be focusing on today. And in the many body problem, the point is that these bandwidths that we're talking about are always extensive, but your frequencies are always order 1, okay? Yep.
What we never didn't get is why is it so important that the series converges? Like, isn't it enough for our purposes that the series is asymptotic in a way, that the gets smaller and smaller?
Right, okay, so let me defer that. So the fact that it's asymptotic actually will enter into the, well, so here the terms may not even get smaller and smaller. That's what I'm saying, because you have all those different bandwidths that appear, right? And then you have all of these different frequencies. So the terms may not even get smaller and smaller if these conditions are not held. Then this point about it being an asymptotic expansion, which is an expansion that looks like the terms are getting smaller but may not ultimately converge, that is actually very important, and it plays a role when we're talking about things like pre-thermalization. So in pre-thermalization, what happens is that it is an asymptotic series, and if you look at the convergence, it looks like up to some optimal order, it looks convergent, and then it blows up. And that optimal order comes with an optimal size, right, because your higher order terms are more and more non-local. By locality, if your system is local and you're trying to probe things at a longer range, it takes a longer amount of time. So in this asymptotic expansion, when you have the optimal order, that defines a time scale for you, and that's what's called the pre-thermalization time. So it looks like up to that time scale, your Hamiltonian or your dynamics is governed by some effective Hamiltonian, but beyond that time scale, everything heats up. Okay, so that the fact that it's an asymptotic expansion actually shows up in a very deep way there. Yeah. So I haven't defined it for you. I'm just saying that you can always do time-dependent transformations into different frames. So here there will exist a frame in which you can look at the problem, like you just do like when you're doing the interaction picture, for instance, right? You can look at things in a different frame. So when you do that, then this Magnus expansion may look convergent. Okay, it's not guaranteed, but if it does, then you can get these new kinds of flow K phases in some sense. Okay, so in the many body problem, which we'll now do, okay, your bandwidth is extensive and your frequency is order 1, okay? So in this repeated zone scheme that we were making, if H again looks like H naught plus V cosine omega t, or just H naught plus V of t, what you start by doing is you have some spectrum of H, okay, of H naught. You fold it down into some bandwidth, which is omega, okay? So all these levels that you had, this is super dense, right? Because this is 2 to the L. If you have a spin system in one dimension in size L, you have 2 to the L many body levels in a bandwidth of size L. So these are exponentially small many body spacings. You take this whole thing, you fold it down into this region of size omega. So generically, you have tons and tons of overlapping levels. And now these gaps will open under the action of this V, and you get all your many body states mix like crazy, and you get heating to infinite temperature, okay? So this is one intuitive picture. There are two other intuitive pictures you can think about. The first is that thermalization, right, by definition almost, is the tendency of a system to go towards equilibrium, and the equilibrium is the maximum entropy ensemble consistent with the constraints in the problem, right? So when energy is not conserved, okay, so usually the maximum entropy ensemble, if you have something like a Hamiltonian, is the Gibbs state, which is like rho equals e to the minus beta h. But now energy is not conserved, so if you have no other conservation laws, the maximum entropy ensemble is literally just the identity, and that looks like e to the minus beta h with beta equals 0. Okay, so that's colloquially why we say, colloquially, you say that the system heats up to infinite temperature, but in reality, there is no notion of temperature because energy is not conserved anymore. But this is what we mean when we say that, okay? That all your observables, all your correlation functions tend to values that they would tend to if you were in the infinite temperature Gibbs state. Okay, the other way to think about this intuitively is if you have a system like this, then if you could think about doing linear response theory. Okay, this is of course very old physics now, and in linear response theory, what you would say is that okay, if this drive was weak, your system would absorb energy from this drive linearly in time, and what you'd get is something like dE dt is let's write this as a cosine omega t times some driving operator. You'll get that dE dt is something proportional to a squared, that's Fermi's golden rule, omega, phi of omega, and this is the dissipative part of the linear response function. Okay, and this we can just define in the usual way. I'm writing this for completeness, but we won't use it. Okay, so this is saying that if this was our system and you started in some equilibrium ensemble of H naught at some temperature beta, and you wanted to know what happens to this system under the action of some weak drive like that, then you appeal to linear response theory and you say that the linear response function will have a dissipative part and the energy absorbed by the system will be proportional to that dissipative part in this way, and over time your system will keep absorbing energy from this drive and eventually heat up to infinite temperature. Okay, so if we want to try to get new kinds of Floquet physics, new kinds of phenomena in this many body system, we essentially need some way to prevent this march towards heating. Okay, we need some way to prevent this heat death. Okay, and that's going to be the subject of Floquet many-body localization. So I'm now going to take a detour away from Floquet, and in the next, for the majority of this lecture now, I'm just going to think about many-body localization and explain to you what that is. Okay? Good. So now we can go to the slides. Okay, so I am going to switch gears now. So are there any further questions on the recap before I do that? Yeah. 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 Sum the divergence. Yeah, so you do sum the divergence. You do sum the divergence series and you try to find what's the optimal order. And that depends on which frame so this is again not an unique expansion. So depending on the problem that you're interested in. So for instance, there's a lot of recent interesting work on pre-thermal time crystals. So in those settings, you don't have an asymptotic time crystal, but you have a time crystal out to some time scale. And if you just did this naive Floquet expansion, you wouldn't see it. But then you can do a different one, and in that you can show that, if you sum the series out to some optimal order, you'll get the response that you desire, but if you go beyond that, you don't. So there's a lot of freedom in which frames to use, and a lot of that just comes down to creative, like you have to play around with it. It may not be a priori obvious what's the right thing to do. Yeah.
Yesterday when we said it, we defined our state as a Fourier expansion, and then we had this microdynamics, you called it, right?
Right.
Same as the block.
Yeah. No, so I won't need that for now. So let's discuss that in the discussion section because that's off topic for today's lecture. Okay, yeah, all right. Okay, so now in thinking about MBL, I want to go back to this picture that we had. Go back to conventional textbook statistical mechanics. Okay, so in textbook statistical mechanics, the picture that we're all taught in high school or undergrad is that you have a system, and for the system to reach thermal equilibrium at late times, you always use this device of a reservoir or a bath. So you say you have the system, it's in contact with some bath, it's exchanging energy and particles, getting entangled with this bath, and as a result of this, at very late times, the system reaches thermal equilibrium. Implicitly, what you're doing there is saying that a time average over all possible states that the system can be in can be replaced by an average over macroscopic equilibrium states, okay? That's the ergodic hypothesis. And when this is true, then you get this equilibrium state. It's characterized by a small number of parameters corresponding to the conservation laws in your system. These could be energy, if you have, these could be temperature if you have energy, or a chemical potential if you have particle number conservation. And using these, you can compute observables. These could be correlation functions, order parameters, whatever you want in these equilibrium states, and use that to describe your system, define phases of matter, okay? So this is well and good. It's, really the foundation that most of our modern understanding of phase structure is built on. But you can ask, what can we say, just as a matter of principle, what can we say about isolated many-body quantum systems that are undergoing unitary time evolution? Okay, so as a matter of principle, this is an absolutely fundamental question in quantum statistical mechanics. You have the system and the bath, but you could just define a new system with the system plus the bath, and that system as a whole will be undergoing unitary time evolution. So you need to ask how does statistical mechanics work in that setting? I can just combine our entire universe and think of it as one system undergoing unitary time evolution. So what is statistical mechanics? What does thermodynamics mean in that setting? Okay. So that's the most general framework. There's no longer a bath. I just have some system defined by some density matrix evolving under a unitary. Okay. This unitary could be that which is generated by a time-independent Hamiltonian. It could be a Floquet unitary, like we've been talking. Some things that people have been studying a lot recently are random unitary circuits. So these are even more abstract unitaries that just keep certain minimal ingredients. Okay, but I'm not going to care about what exactly the unitary is. It's just that it's unitary time evolution. Okay. And in this setting, we have in mind strongly interacting, very highly excited systems. Okay, so there's no quasi-particle description. These are generic many-body systems. It's not integrable. There are no special conservation laws. They're just generic many-body systems. They could be systems of spins, atoms, qubits. And the point is, the standard assumption of statistical mechanics is that such systems go to thermal equilibrium at late times. But what we want to ask is, must this always be true? Okay. What does thermal equilibrium even mean in this context? Okay, usually when you think of something reaching equilibrium, you have in mind that you can do something very non-generic at early times, and if you wait long enough, then your system settles down into some equilibrium state, and memory of what you did at early times is lost. Your late time state is only characterized by a few small number of observables. But if your system is undergoing unitary time evolution, then in a detailed mathematical sense, there can be no information loss under unitary evolution. So the system as a whole is remembering all information about its initial state for all times. Okay? So what does reaching equilibrium even mean in this context? And then you can ask, when systems do reach thermal equilibrium, how is that thermal equilibrium reached? What's the process that's happening? Okay, so there's many questions in this, in this general framework, and we'll touch on just a few for the next hour or so. Okay, so this question, even though it's this question not only is this question very fundamental, it's actually very topical because of great progress that has happened in the last decade or so in engineering isolated many-body quantum systems in various platforms ranging from solid state to cold atomic. Okay, so these are systems of ultra-cold atoms, nitrogen vacancy centers, trapped ions, Rydberg atoms. All of these platforms together have been working very hard to create isolated quantum coherent systems that don't interact with the environment. Okay, even the quest of building a quantum computer. What is a quantum computer, right? It's an isolated system that's doing some kind of quantum computation, and the general thing that you worry about is decoherence, but the effect of decoherence is precisely the effect of the environment. So when you're trying to make this quantum computer more and more coherent, what you're really trying to do is make it more and more isolated. Okay, so this is really a very topical area. Okay, but and because of this great progress in these experimental platforms, attention has focused on these questions that I was listing very sharply only in the last decade or so, but really these are questions that go back to the foundation of statistical mechanics, so there's nothing fundamentally new about these questions. And indeed, Phil Anderson, in his Nobel Prize-winning paper where he was describing Anderson localization, which we'll talk a lot more about, was already anticipating this question, okay? So strictly speaking, Anderson localization only applies to non-interacting electrons. That's what he proved his theorem for. But he really had in mind physical systems that had interactions, okay? So the question he was asking was very much in the context of an interacting system. And, you know, this is just a blurb from his introduction where it says, second, and probably more important, as an example of a real physical system with an infinite number of degrees of freedom, having no obvious oversimplification, in which the approach to equilibrium is simply impossible. Okay, so he was thinking of real physical systems in which the approach to equilibrium is simply impossible. And third, as the irreducible minimum from which a theory of this kind of transport, if it exists, must start. In particular, it re-emphasizes the caution with which we must treat ideas such as the thermodynamic system of spin interactions when there is no obvious contact with a real external heat bath. Okay? So already in this paper in 1957, Anderson had anticipated the questions that are now really active research areas. Okay? So you have a real system with no real external heat bath, and what does thermodynamics even mean in this context? And does such a system reach thermal equilibrium? Okay? So this question, which really goes back to Anderson 1958, rephrased, says, can an isolated many-body system undergoing unitary time evolution act as its own bath and bring subsystems to thermal equilibrium? Okay, so I've already hinted at the answer that I'm going to get to in a second, but the question is, can this system reach thermal equilibrium? And what we'll see is that there are two generic answers to this question that we know about, okay? The first is yes, your system does reach thermal equilibrium. These are what are known as thermalizing systems. But then there's this whole new class of systems, which is what we're going to focus on, which allow all sorts of new phenomena outside equilibrium, which are your many-body localized or MBL systems, okay? So in these systems, you can start off with some very, very non-generic initial state, and in some detailed sense, the system never reaches equilibrium even at infinite times, okay? So I can take this simple yes-no answer and dress it a little bit, okay? And you can ask that, you know, when you're talking about whether this isolated system reaches equilibrium or not, and you want to use that to define crisp dynamical phases of matter, you want to try to answer this question in some asymptotic sense, okay? So you're thinking asymptotically at infinite times, does the system reach thermal equilibrium or not, okay? And if the answer to that is yes, the system is thermalizing. But you can distinguish between whether this thermalization happens on accessible timescales that you can see in a lab, or if there's some other physics in the problem which causes this time scale to be extremely long. Okay, so this comes back to this notion of pre-thermalization that I've hinted at for a few times. Okay, so even if your system eventually thermalizes, it may take extremely long times to do so, and in the middle intermediate regime, we can get all sorts of interesting pre-thermal possibilities. Okay, or the negative answer is that the system remains MBL for all times. Okay, you can take an infinitely large system and wait infinitely long, and the system never reaches thermal equilibrium. Okay, so the last thing I'll say on this is that there's actually all sorts of, you can ask, what's intermediate between yes and no? Okay, like what are intermediate dynamical universality classes? And this is again a major open research area. Recently, you may have heard people talking about many-body quantum scars. So, regardless of what you know or think of them, they furnish an example of something that's kind of intermediate between fully thermalizing and fully many-body localized. Okay. So let's delve into this question of thermalization and isolation in a bit more detail. Okay. So the point which I was mentioning earlier is that you have a system as a whole, and the system is undergoing unitary time evolution. So as a whole, the system remembers all details about its initial state, okay? But in this setting, when we say the system reaches thermal equilibrium, what we really mean is that the system reaches local thermal equilibrium, okay? Because even though the system remembers all memory about its initial state, this memory can get mixed up or scrambled in very, very non-local global degrees of freedom, which an experimentalist doesn't have access to in a lab, okay? So in some detailed sense, you can reverse your time evolution by acting with the U-dagger operator, But in a practical sense, the information that is remembered has been so delocalized, okay, in this chaotic system that you really don't have access to it in any useful way, okay? So the way to sharpen that, is to say that, you had your system as a whole, but now you can ask, what do local observables in your system look like? And in particular, we can ask, even though there is no external bath, can the rest of the system, in a sense, act as a bath for it? Can the system as a whole act as a bath for itself, okay? So that these degrees of freedom can bring local subregions into thermal equilibrium, okay? So formally, what that means is we have some rho of t, which is given by rho naught u, okay? That's the state of the whole system. From this, we can compute a reduced density matrix by tracing out this whole region here, okay? Rho of t. And the question is, if you wait very long, okay, so you have time going off to infinity, and you have a very large system, so the rest of the system is also going off to infinity, A is local in some sense, okay? Does this reduced density matrix of the system look like a thermal density matrix, okay? And what we mean by that is, if you had a thermal density matrix, which was characterized by, say, some temperature, chemical potential, does this rho A of t at late times approach the right equilibrium reduced density matrix, okay? And when it does, you say that the system has reached thermal equilibrium, and when it doesn't, then it hasn't, okay? And now you could ask, what sets these parameters, right? The temperature, the chemical potential. When you were doing your textbook statistical mechanics, you didn't really have to worry about this because, you had a bath, right? And the bath was this all-knowing infinite reservoir which had a temperature, which had a chemical potential, and then when you brought your tiny little system in contact with that bath, the properties of the bath set the thermodynamic variables for you, okay? But here, it's just the system as a whole, okay? And you just start with some initial state for that system, so what's setting the right temperature, what's setting the right chemical potential, okay? And the idea, the point is that it's actually the properties of the initial state themselves, okay? So what this is implicitly already telling you is that when you're thinking about thermalization, there is a right class of initial states you have in mind, okay? And that right class of initial states are states that have sub-extensive uncertainty with respect to your thermodynamic conserved quantities, so that things like temperature and chemical potential can actually be well defined, okay? So more concretely, what do I mean by that? So if I want to define, let me just write it as beta. If I want to define beta, I want to say that I want my trace of rho naught h, right, which is setting my energy density, to be the same as the trace of e to the minus beta h, okay? So this is saying that whatever your whatever the expectation value of energy in your initial state was, okay, that energy density corresponds to a temperature in the equilibrium ensemble, right? You can ask, if you want to get that same energy density out, what temperature do you have to use? And that sets the temperature that you're going to thermalize to, okay? Yeah.
So the play ergodicity explicitly then
Right
here?
now there's no ergodicity. This is the definition of ergodicity in a closed system.
But if you are referring to the memory of the initial condition.
Okay. But that's true whenever you're talking about thermalization, right? That detailed memory of your initial condition is lost. Only some coarse-grained memory about what was the temperature, what was the chemical, only some macroscopic memory corresponding to a few global conserved quantities is preserved, okay? And that's what we're saying here, that in this local sense, okay, locally, no matter what you did to your initial state, all of that is lost. But all you remember is some global properties of temperatures, chemical potentials, and you're thinking about generic systems where there's only order 1, just a few global conserved quantities. So this is not breaking ergodicity in any way, okay? And when I write an equation like this and use this to extract a beta, what I'm implicitly assuming is that the temperature is set by the energy density of the system, okay? So beta is conjugate to E over V, okay? So what you're implicitly assuming is that the energy density of the system is a well-defined quantity. And what that means is that delta E over E should go to 0 as V goes to infinity, okay? So normally when you're thinking about thermodynamics and fluctuations, the typical answer is that, from delta E goes as square root of volume, E goes as volume, so delta E over E goes down as 1 over square root of V, okay? And you have a well-defined energy density. And vast classes of initial states, okay, for those of you who are a little bit more expert, any short-range correlated initial state that you can write down in a system which has a local Hamiltonian will satisfy this property, okay? So good. So almost all physically preparable initial states, vast classes of initial states, all of which have a well-defined energy density, a well-defined number density. You can ask this question about whether those states will reach thermal equilibrium with respect to local observables, okay? And now we can go and ask about a strong versus weak form of thermalization. Because the point is that if all sensible, okay, and by sensible I mean states which have well-defined expectation values for these conserved densities, if all sensible initial states reach local equilibrium, okay, then this actually implies a strong version of what's known as the eigenstate thermalization hypothesis, okay? And why is that? Because the eigenstate thermalization hypothesis is really the crux of how we think isolated systems reach equilibrium, okay? And what it tells you is that in an isolated system, every individual many-body eigenstate individually looks thermal, okay? So every eigenstate has information about the right thermal ensemble in your system, okay? Because why am I saying this, right? So in an eigenstate, you know that the expectation value of your Hamiltonian in this eigenstate is En, and we know that delta En in an eigenstate is just 0, okay? So this is a well-defined state with some energy density and 0 uncertainty in energy, okay? And we know that this is a time-independent state. So if you want to say that all states that have this kind of property, if you wait long enough, reach local thermal equilibrium, well, in an eigenstate, you don't have to wait at all. It's already, in the state it's going to be. But then this tells you that local observables computed in eigenstates themselves agree with the right thermal equilibrium answer, okay? So what that means is that if you compute some local observable which lives in A in the eigenstate, this equals trace of OA e to the minus beta n h with 1 over z, okay? And this beta n now is set by En over V, okay? So usually we're used to thinking about canonical and microcanonical ensembles, okay? So the canonical ensemble is like this Gibbs ensemble where you're averaging over all these different states. A microcanonical ensemble says pick some fixed window of energy and average over the states in that window, and you say that the two answers should agree, again, up to fluctuations that go down to 0 in the infinite size limit. But what this is telling you is that for your microcanonical ensemble, when done in the eigenbasis, you actually don't even have to do this averaging over some states in some window. Individual many-body eigenstates form a decent microcanonical ensemble, okay? So that's the punchline of the diagonal ETH. I'm not going to go into off-diagonal ETH, but diagonal expectation values computed in many-body eigenstates agree with the right thermodynamic ensemble, okay? So this is still a hypothesis. It hasn't been proved in full generality, but there's numerical evidence for this in large classes of many-body quantum systems. And a plot for ETH, this is real numerical data, will look something like this. Okay, so what's being done here? It's very simple. You take a many-body Hamiltonian, okay, which is interacting. You expect it to thermalize. It's not integrable in any way. You get its entire spectrum, so you get its eigenvalues and eigenvectors. Those are these guys. You compute some local observable in all the eigenvectors. And what you find is that this observable is a smooth function of the energy density of the system. Okay, so each blue dot represents one pair of ON and EN, okay? And you see that it actually follows this very smooth dependence with some fluctuations which are quite small and actually go down exponentially in system size. And the value about which, this curve is actually the same as the trace of O evaluated in a Gibbs state with temperatures of the Gibbs states chosen to match the corresponding energy densities. Okay? Yeah.
This Hamiltonian of the whole system, A plus B.
Correct. But the O is just some local observable.
Okay, but O is the observable belongs to A.
Correct. Okay. Because if you want observables that live in the system as a whole, then you know that a whole bunch of observables exist that will never equilibrate, right? And these are just, you can just write down the projectors onto different eigenstates, right? These are usually horribly non-local objects, and you know that these are all constants of the motion, okay? But because these are so non-local, they don't constrain your dynamics in the same way that an integrable system has its dynamics constrained, okay? So the point is just that you have your system as a whole that has all of these eigenstates. Those are eigenstates are treated as these states here, which are the states that are in the system as a whole. And now when you compute local observables in those eigenstates, which was this rho A of T, okay, those agree with the correct Gibbs ensemble.
Would A and B interchange? Could we B instead?
Okay, good. Good. So the question is, can A and B be interchanged? So all of this is, you really want B to act as a bath for A, okay? So in principle, the way we're thinking about this is that B is much, much, much bigger than A, and you want to think of B going off to infinity. Now you can ask, how big can you make A and get away with it, okay? And that's still an open question. For many properties, like when you compute things like the entanglement entropy of the system, for some entanglement entropies, we found that you can make A as large as half the system, and it still works, okay? So that's more empirical observation rather than proof. But in principle, you should think of A as being much, much smaller than B, okay? Yeah. Oh, it's this. There's no, this is the conjecture that this work. This is the conjecture.
So the conjecture is that every system that thermalizes.
Correct. But before someone wrote this down, you wouldn't know how to answer the question of what does thermalization mean in a closed quantum system.
But then there's no hypothesis, just definition.
Well, no, because there's again, like you have to go from. There's various things you can do, right? Because these are what the eigenstates do. Now you can start asking about, do all initial, you could have cases where not all initial states thermalize, but the vast majority of them do. What does that mean for the eigenspectrum? So yes, it's one-on-one, but it's the fact that, the hypothesis is that a generic quantum system will obey this, right? And it will reach thermal equilibrium, and that a generic quantum system will obey this for all eigenstates. And there's a different part of the hypothesis which I'm not going into, which is how off-diagonal operators behave, and that tells you how the approach to thermal equilibrium happens, okay? So it's really like, and this part is more of a hypothesis because it's telling you that your eigenstates at high temperatures really look like random vectors in some sense, and we already know that there are various corrections to that, okay? So it's really, it is a conjecture for how a generic many-body system reaches thermal equilibrium without any reference to the details of that system, okay? And the amazing thing is that there are vast classes of systems where this has actually been shown to be true, even though, yes, exceptions exist, and we're trying to come up with a framework that's universal enough to keep all those, to have all those exceptions possible, okay? All right, yeah.
Just a point that I didn't understand very well.
Yeah.
What you call demand, the eigenstate,
Yeah.
does it have to do with the dimension of the system?
Which n? This n? No, it's just a number of, it's just an index of the eigenstate. Yeah.
So this graph is telling me nothing about what happens if I increase or change the dimension of the system.
Not this graph. So n basically goes from 1 to 2 to the L if you have a spin 1/2 system. Okay, so that's how many blue dots there are, is your system size in that plot. Okay, so in a spin 1/2 system in 1D of length L. Right, because your Hilbert space dimension is 2 to the L, that's how many eigenstates you'll have. But so the part of this plot that I didn't show you is that you can actually make this plot for different system sizes, and you can ask how it converges to this distribution. And the point is that, if you make it for some small system, you'll actually see a pretty wide distribution, but then you'll see as you keep narrowing your system, this converges more and more, okay? And this narrowing is actually exponential in system size, okay? So system size. It scales with the inverse Hilbert space dimension to some power, okay? Good. So, yeah. Yeah. That's right. Well, so right now I have in mind a unitary that's generated by a Hamiltonian, because I'm writing things like e to the minus beta h, and that refers to a Hamiltonian. Yeah. Yes. No, but that's the point of which it's a conjecture, it's a hypothesis, so that's what I was saying, that, it could be the case that almost all initial states reach thermal equilibrium, but there's some vanishing fraction that don't. That actually happens in systems called, which are these scarred systems. So you're absolutely right. Like this, the conjecture is that all sensible initial states, and by sensible I mean, with these sub-extensive uncertainties, will reach thermal equilibrium. But we already know exceptions where that doesn't happen. So, but that's the strongest version of thermalization, that this would happen for all of them. But you're right that proving this for any given actual Hamiltonian is notoriously difficult. Yeah. Okay. Yes, absolutely. Yeah. 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 Exactly. Yeah. That's right. That's right.
Then the picture here is totally that of a pure system, right?
Is totally what?
This is the picture of a pure state which is evolving.
No, but the pure state the pure state is a state which is at some temperature, right? So this beta was determined by the temperature of the state, right? So the pure state is at some energy density, and you know that for your Hamiltonian, if you draw something like entropy versus energy, right, it has some density of states which looks like that. So then depending on the energy density of your pure state, which sets the temperature of your pure state, you'll figure out whether you're in this part of the spectrum, or this part of the spectrum, or this part of the spectrum. Why does it? It depends on the temperature. Like, what's the right equilibrium ensemble you're going to pick, right? And so fluctuations, you know that the fluctuations go down as the fluctuations is 1 over square root of v, right? That's a function of the entropy density, and the entropy density cares about the temperature. So it's really just when you're doing normal statistical mechanics, right? You have an entropy, you have a energy, you have fluctuations. The fluctuations are scaling as some inverse power of entropies, right? So it's exactly the same thing. Yeah. Yes. Multiple eigenstates of what that matter? No, but what this is saying is that you can pick all global eigenstates at the same energy density. That's what this is saying, that if you fix your global energy density of your system, that fixes a global temperature of the system, that fixes a relevant Gibbs ensemble, okay? And you know that for the Gibbs ensemble at a particular temperature, this observable O has to take some value. That's set by this curve, okay? And then all initial states or all eigenstates which have that same energy density corresponding to a given temperature beta thermalize to the Gibbs ensemble at the right beta. Yeah.
Maybe relevant to this question, could you please write a rho for the total system?
Yes.
Before, so the
Yeah.
beginning
Sure. So that is this. So this is rho naught. Okay, that's rho of t. Fine. So rho naught is that. Okay.
And that would be, let's say, that's local for A, right? Or
No, it's just some initial state. It's just some initial state. All you need from that initial state is that it has a well-defined energy density. Okay, so it could be an eigenstate, which has a perfectly well-defined energy density, or it could be some other generic state that an experimentalist can prepare. Okay, so that's what rho naught is. Your time evolving the entire state under unitary time evolution. So if you started with a pure state, it remains pure. Okay, the state had some global energy density, which is conserved because that's a constant of the motion. It had some global number density, that's conserved because that's a constant of the motion. The energy density and number density of your initial state define for you the correct Gibbs ensemble parameters, which is the beta and mu naught. This is really set by the initial state. And then what you say is that if you now want to compute local observables, you can basically work with this Gibbs ensemble.
okay, but rho A is maximally mixed now.
Well, it's mixed to the extent that this object, it's mixed to the extent that it is mixed, that's right, but it's going to be mixed to the extent that the entropy of rho A is going to be set by the equilibrium entropy.
Okay, so had I begun with a pure state for A, let's say,
Yes,
I would still end up with the maximum
correct,
state.
because A is getting entangled with B.
Okay,
Yes.
but the sort of equilibrium, like the properties will be still defined by this hypothesis, like so the
Yes.
sort of the Gibbs or whatever.
Yes.
Thermodistribution.
Yeah, yeah. I mean, the way you should think about it is that when you were doing textbook statistical mechanics and you talked about a system reaching thermal equilibrium due to talking to a bath, the way that's happening is that your system is getting entangled with the bath. When you trace out the bath and you look at the system alone, you are left with a Gibbs state on the system, which is a mixed state. Here, even though the system as a whole is undergoing pure state evolution, your subsystem A is getting entangled with your subsystem B. And when you trace B out, you say that B can act as an effective bath for A, and A reaches thermal equilibrium.
What is the difference then, I mean, between the standard, like the mass
Yeah.
equation and
Yeah.
like, why do we care that much in a sense?
Well, but the point is that
What the mass is, yes.
No, but that's what I started this whole discussion with, right? That like, usually you always treat this bath as something so fundamental, right? You know, you open page 5 of a textbook in Stat Mech and you're already invoking the bath. But really you could have thought of the system plus the bath as a unitary system as a whole, and then you can ask, okay, where do you go, right? Like, are we going to create some like Russian doll of baths, or can we just look at something like this? Okay, that's a great question, and that hasn't in some cases, like when you have a Lindblad evolution, you can show that the thermal density matrix will be a steady state of the Lindblad evolution. But if you just have a generic quantum channel, as far as I know, I don't think it's really been shown. Yeah. Okay, all right. So, okay, we should go on the break soon. So I have 2 slides before the break. Okay, so the other thing that the eigenstate thermalization hypothesis implies for you, okay, is that the von Neumann entropy of subsystems. Okay, so what I was saying here is that you can compute an observable and it agrees with what it would in a Gibbs or a thermodynamic ensemble when your system thermalizes. So what this means is that the von Neumann entropy of some subsystem, okay, that's the entanglement entropy. Really all of this is coming from A getting entangled with B. So the entanglement entropy of your subregion A, which is defined in that way, right? You can take the reduced density matrix of A and get an entanglement entropy out. And the von Neumann entanglement entropy of a subsystem has to agree with the thermodynamic entropy. Now, we know that the thermodynamic entropy is an extensive quantity, okay? So what this tells you is that when B acts as a bath for all spins in A, this von Neumann entanglement entropy of A scales with the volume of the subregion A, because your thermodynamic entropy is extensive. So this von Neumann entropy is extensive with some coefficient, which is the thermal entropy density, okay? Which is again set by the relevant temperature. So this is what is known as the volume law of entanglement. Okay, so all finite temperature initial states which is, if you're at a finite energy density, you're at a finite temperature. If you're at a finite temperature, you have a finite entropy density. So all finite temperature initial states, or all finite temperature eigenstates in a thermalizing system have a volume law entanglement entropy for subregions, okay? So when you hear people talk about volume laws and area laws, this is what volume law means, okay? And now, when we come back from the break, we will talk about many-body localization, which is the only generic exception to thermalization that we're aware of, okay? And by generic, we mean systems that are not fine-tuned to any way. It really defines a phase of matter that is localized. You can take a localized system, perturb it weakly, and the localization remains, okay? So that's why we're not talking about integrable systems, even though those also have extensively many conserved quantities and don't reach equilibrium in this usual way. They thermalize to what are known as generalized Gibbs ensembles, okay? So localization, as best we know, occurs in systems that are not translationally invariant, so they are disordered or quasi-random or quasi-periodic systems in some way. And in these systems, the system as a whole retains local memory of its initial conditions to infinitely late times, okay? So we say that the system acts like a quantum memory, okay? So what we were saying here in a generic thermalizing system is that even though globally information is preserved under unitary time evolution, locally your subsystem only remembers some coarse-grained properties like temperature or chemical potential. But in an MBL system, locally your system remembers local memory about all these details of your initial state forever, okay? So that's the sense in which it acts like a quantum memory. And this kind of, so this really, the existence of MBL leads to this new kind of phase transition, a dynamical phase transition between systems whose dynamics at late times bring it to thermal equilibrium in this local sense, and others that don't, okay? So this is a brand new kind of transition that we're really still really grappling our heads with and trying to get a handle on, because this is a phase transition where on one side of the phase transition, equilibrium statistical mechanics holds, and that's the framework we usually think of for defining phases. But on the other side of the phase transition, StatMech itself breaks down, okay? So this is a phase transition that really involves the restoration of statistical mechanics, and really how to think about that is something that's very, very open right now, okay? And the punchline that I'll get to in the context of Floquet physics is that many-body localization can stabilize new kinds of order that may be disallowed when you have these strictures of equilibrium thermodynamics, okay? So our capstone example for this tomorrow will be Floquet time crystals, okay? And this is just a picture that I'll leave you with for an actual experimental system in a cold atoms group in Emmanuel Bloch's lab that I was involved in. And this is, the experiment, when I was defining phases of matter or dynamical phases of matter, I have in mind these asymptotic limits of infinitely late times. A realistic experiment, of course, cannot go to infinitely late times, but within the parameters of that experiment, let me tell you what they did, okay? So they prepared two classes of systems, okay? In one, they tuned the parameter. This is like some kind of effective disorder strength, and I'll show you that disorder is actually very important to get MBL. They tune some effective disorder strength so that all your atoms, this is in some atomic trap, all your atoms started off in the left half of the system, okay? So this is what it's showing at time t equals 0. And then you let your system run in time, okay? So the colors are a bit hard to see. Is this the light? Okay. So you see that, at time t equals 0, you prepare your system with all the atoms in the left half of the trap. And of course, if you imagine that your system is going to thermalize, if you start this room with all the atoms in the left half of the room and you wait long enough, what you'll say is, of course, you reach some mixed equilibrium state and all your the density at late times becomes uniform, okay? So indeed, for this set of parameters, if you wait long enough, this is the lifetime of the experiment, what they find is that, it looks isotropic within the trap and, your initial imbalance has been forgotten. But if you look at this set of parameters, which has strong disorder, and you wait, what you find is that even at these late times, you have preferentially more atoms in the left part of the system than the right, okay? So you prepared this very, very non-generic initial state with all these atoms piled up, and even at very late times, you can just go in and measure some local density, and that shows you that local memory of that initial imbalance is preserved for this time. okay? And in theory land, we would say that, you know, this system is MBL if you can take this time of 249 tunneling times and make it infinite. But the fact that you can even see this in an actual experiment today is really remarkable, okay? All right, so let's leave that for the break. All right. Yeah.